And what I wanted to do for this session is tell you some things about how the solvers work. So let me what the point of it is first, because sometimes it's not totally apparent. So the reason to understand these things about solvers is kind of the same reason to understand the way that your lab instruments work. You don't have to be able to build your lab instruments for the most part. You just run them, but you need to understand the characteristics so you understand what comes out and when they might be getting into a situation where they're not giving you reliable output. I like to say that when I was in the lab, I had a lock-in amplifier, and I don't know how to build a lock-in, but I do know how it works. It works by multiplying two signals together, a carrier wave and an input signal, and you average them over many periods, and that extracts the part of the input signal that's near the carrier wave, because all other Fourier components are orthogonal. And then if you understand what your input impedance is and what your output impedance is, then you can see what the limits of your machine are. And you can see what signals might you be able to extract from noise that way. And the same thing applies for the solver. We want to understand what the characteristics of the solver are so that we understand when it's working well, and when it's not working, what we might do to fix it. But the intent is not to go over the mathematics, which I don't think is very enlightening. It's more like to go over the engineering. Okay, so the package that we use for solvers is called PETSC. It's a fairly old package. It's 22 or 23 years old, and it solves sets of linear and nonlinear algebraic equations. It has a bunch of different solvers, both what's called direct and iterative solvers. Oh, these are the old. I uploaded the old version before I changed it. The date. Oh well. I'll live. The new version is on the website. Okay, so as I said, we want to enable you to both assess solver performance and then optimize or fix particular problems. So first we want to talk about how you control the software. You control the solvers the same way you control everything else in PyLith, which is by these options. And so directly to PETSC, the options have this form above. So I can set the type of linear solver or the type of preconditioner, and I'll try to explain what those are. And in PyLith, these are just specified as PyLith type options with the prefix PETSC. So I think this is our plan for handling all sub packages in PyLith, is that you'll preface the option by the package name when you need to get directly to it. I'm going to illustrate stuff directly in PETSC a little bit, just because we have very, very simple problems, simpler than PyLith has set up for you to look at. And then I'll do it directly on one of the PyLith examples, PyLith Hex 8, which I think just has it's just a cube with a fault down the middle that we shear from both sides. Okay, so how do you begin learning about these things? So I think the most important kind of solver to understand is what's called a Krylov solver, and here's why I think so. I said there were two kinds of linear solvers, direct and iterative. The nice thing about direct solvers is that they either work or they fail in a spectacular type of fashion. And so it's not hard to see what's going on. There's very little you can do about it. There's not much you can do to help a direct solver, but they're easy to understand. So the prototypical direct solver is something like Gaussian elimination, also called LU decomposition. But since they're so easy, you really don't have to worry about them. The problem, you might ask, why don't we always use direct solvers? We don't, because the memory requirements become onerous, and in fact, you just run out of memory before you can solve practical problems that you might want the answer to. And this is why we turn to iterative solvers. Now, sometimes iterative solvers are also faster than direct solvers, but not all the time. But definitely, they always take less memory, and that turns out to be the real limiter. So, the most popular kind of iterative solver, there are different iterative solvers, but the most popular kind is what's called a Krylov solver. And Krylov solver is something which builds a small version of the problem and solves that small version. So exactly how does this work? Well, and this is something that is useful to understand. How might you build a small version of a problem? And this is not something confined to this Krylov solver in particular. Others of you may know the term model reduction. So model reduction is exactly the same thing as a Krylov solver. Here's how it works. You have a large problem, and let's say this is a large linear problem. So you have a large linear problem which can just be expressed as a matrix equation, AX equal B. So you'd like a small version of this so that you can solve it, because the large version is too big to solve. So what do? Well, let's say that you picked a couple directions, and you said, I'm only going to solve in these directions. Okay. This is what is happening here at the top of the slide. I have an operator a matrix, and I have a residual vector, which is just the residual is the amount that my equations are not satisfied. So here it's AX minus B. If I had the exact solution, that would be 0, so I would have 0 residual. A residual is kind of like the companion to the error. The error is how different is my solution from the true solution, and the residual is how different is my satisfaction of the equations from 0, because the exact solution will give you 0 in the equations. So I have a matrix and the residual, and I'd like to make a set of vectors on which to project. And so these define my tiny subspace that I want to solve in. And what I do, since I only have A and R and nothing else really, I just keep multiplying R by A. And you can prove that this generates a series of vectors. It doesn't repeat. Or if it does repeat, then you can prove that the solution actually lies in that tiny space before repeating. So what you do is you form that set of vectors, and then you project A down into a tiny problem that's only that's spelled incorrectly. That's only present in that small subspace spanned by those vectors. And then you solve that problem, and you can solve it with Gaussian elimination or other methods that are guaranteed to work because it's so tiny. And then you project back into the full space, and that's some approximate solution. The reason this is an iterative method is you can keep making additional vectors to get closer to the solution. So, are there any questions about what a Krylov method is? Okay. Good. So why do we use them? Well, they can be very, very useful. They handle what's called low mode errors. Now, what does that mean? Low mode errors are errors that span a good fraction of the domain or the whole domain. So very slow fluctuations across the entire computational mesh. Now, because it's very easy to correct local errors. You can go look at a small spot and sort of do some small manipulations and get rid of the error in a tiny position. But it turns out that the hard errors to get rid of are errors where you got a slow oscillation over the entire domain, and that's what you need these more sophisticated solvers for. However, they aren't good at the local parts, so you need what's called a preconditioner, and what the preconditioners often do are handle a lot of the local solving to get rid of the high frequency errors or the very local errors. However, Krylov methods, the way that they are able to handle these low mode errors is through orthogonalization. They build an orthogonal basis for the small subspace. They project orthogonally or semi-orthogonally your problem into that subspace. And so they do a lot of inner products. And inner products are costly on today's hardware, especially on parallel machines. What is the reason? If you think about doing a dot product, you take two vectors, you multiply all of their entries together, and then add them all up. It's the last step that is costly because everyone has to talk to everyone else in order to add up all the numbers. And also, everyone has to know about the solution. Whereas if you just add two vectors together, each processor can know about only its own part of the vector, and you're fine. So it's this global knowledge that's costly, and that will tend to decrease the performance of these kind of methods the bigger your machine gets. So, as I said, Krylov methods do not work on their own. So, unfortunately, you cannot just learn about the iterative solver. You also have to learn about what's called a preconditioner, which is very often another iterative solver. So, the message is that we usually have to use several different kinds of solvers put together in the right way to achieve a good result for these complicated equations. For simple equations, you can pick a good solver, a single solver that will work, but that's almost never true for realistic equations. And so what we do is we pick a few solvers that fit together correctly, each handling a different part of the error or a different part of the physics, and that combined solver can be effective. So this is where you get it. This is where the algorithm engineering comes in, figuring out what solvers do I need, how do I put them together. The normal way you think about preconditioning is the preconditioner should be inexpensive and it should accelerate convergence. I think that inexpensive might now be the wrong way to think about it. Really what we want is each solver that we use, each subsolver, I guess, should accelerate part of the convergence. The Krylov method takes care of some of these low mode errors. Multigrid takes care of all the high frequency errors, and then the successively coarser grids take care of lower and lower mode errors, and then at the bottom the Krylov method is working. So these are better ways to think about how these are put together, I think. So now I want to talk about how I would actually go about dealing with a solver when you have to do science. So always start with a direct solver. Why? Because you should always be starting with a problem that is small enough that a direct solver can solve it, just so you know what you're doing. They have no tolerances to mess with. They have very little dependence on the problem itself, and here I say condition number, but they don't depend very much on the problem or the physics for getting an answer. And it's a great way to check that your problem was well posed, or here I say not singular. because you can evaluate the error very, very simply. And so I would always begin by solving the problem with LU, and then slowly change over to a less and less accurate solver till you get to the point where you are satisfied with the accuracy and it's running fast. Because if you start with the direct, you can check all the things like your physics, your boundary conditions, that you can produce the phenomena that you're looking for, and then you can scale up. It's possible, so the built-in LU that we have in PETSC is just runs in serial, or just runs on a single processor. If you can continue to run on multiple processors, actually, by using one of these packages, MUMPS or SuperLU. These can be downloaded automatically when you configure PETSC by providing these options to the configure process, and they can be selected as solvers the same way by giving an option. So it would be nice if that was all there was to it, but there are some complications with using the direct solver that I want to go over, because I think it is really important that you start with the direct solver. So two complications are that the problem can be singular, and the problem can be indefinite. And here I say a saddle point problem, and that's what's going on. It's indefinite, meaning that it has both positive and negative eigenvalues, and another way to say that is that there are some zeros on the diagonal potentially. So for saddle point problems, we use a special solver that knows about the structure. So where do saddle point problems come from? Saddle point problems come from a lot of times systems with constraints. So in PyLith, if you have a fault, we're imposing a constraint across the fault. Here it's a constraint on the separation between a node on one side of the fault and a node on the other side of the fault. So for instance, if you had a kinematic fault description, those would be fixed. If you have a frictional fault description, the constraint will be that the force necessary to get that separation agrees with the Lagrange multiplier, right? So if you have this structure, then we can decompose the problem and run a direct solver on the different parts of it and still get the exact answer. And that's what we want to do. It turns out that PETSC can do this automatically using this option here. PC is the standard prefix for any preconditioner. So if you use the field split preconditioner, which means decompose the problem into blocks, detect a saddle point, which it will, and detecting is easy, it just looks for zeros on the diagonal of the problem. Then it can pull it apart into blocks, do a direct solver on each block, and put it back together. And this process is called a Schur complement. And so it will automatically do Schur complements if you ask it to, and this is what you need to do. You need to ask it to do this. I will do all of these in an example. So we will see this. But this is what you need to be aware of. It's hard to know whether to do the examples right when I'm talking about this, or to save them and do them in a row because there's more continuity. So I've chosen to save them, but we can always go back to these slides if people have questions. Okay, so I said when you begin, use a direct solver. But of course, I also said that to do practical things, you cannot use a direct solver. So what do you do once your initial problem runs with LU? Well, the first thing to do is to look at how it's running. So if you have LU, you should always get one iterate. If you don't get one iterate, then something is quite wrong. Probably you have made a mistake specifying boundary conditions or some such and made an almost singular problem. So the first thing to be able to do is know what solver you were running. So if you give the SNES view or KSP view options, this is for nonlinear and linear solvers, it will output a full description of the solver that you use to run. And of course, in PyLith, you would say --PETSC.KSP underscore view. So here it says we have a linear solver. I should use the arrow, I guess. Where's my, I just have to click on it. There we go. So here it says we have a linear solver. Now what's this? This is the prefix. And the prefix allows you to control each part of the solver individually with PyLith options by giving this particular prefix. So let me give you an example. Here it says that it had a maximum number of iterations of 1, which is very small. And you might want to use something like 100 or 1,000. Well, how would I do that? Well, I would give the option --PETSC.KS field split underscore 0 underscore KSP underscore max underscore it equal 100. And so you can reach in with options and using options prefixes and control any specific part of the solver that you want. This is very, very similar to the way that you can reach in with a properly namespaced option and control any part of PyLith itself that you want to control. And here we say here are the tolerances, the relative tolerance on the residual, the absolute tolerance on the residual. Here we say right preconditioning. I don't think it's terribly important to know the difference. There are two types of preconditioning, left and right. However, I do think it's important to look at this. Has attached null space. So what does that mean? Certain kinds of solvers need to understand the analytic structure of your operator. So let me give you an example of this. The elastic operator, the pure elastic operator, has, let's say in 2D, has a null space of size 3. Why? Well, if I translate my entire system in X, it does not change the energy. If I translate it in Y, it does not change the energy. And if I rotate it around, it does not change the energy. So you can't tell the difference between my system and one that has been translated or rotated. This is also true in 3D, except you have 6 ways you can do this: 3 translations, 3 rotations. So the question is, then, when you are building solvers for this, how do you tell the solver that you have this kind of degeneracy? Your boundary conditions remove this degeneracy in the full problem that you specified to PyLith, but the solver works on little parts of the problem, and the little parts of the problem have all these degeneracies, and it's only the full problem when it gets put back together with the boundary conditions that you remove them. So we need to tell the solver about these, and the way you do it is you attach a null space. And it's a null space because when you act with the operator on a translated or rotated configuration, you get no change in energy. Oh, and I should show that it also tells you how many processes you're running on, which is useful just as a check if you're running in parallel. So these were views, like KSP view. There are also monitors, like KSP monitor. And what the monitors do are give you running feedback as the solver is working, instead of reporting on what the solver was. So, for instance, if you had a nonlinear solver, like Newton's method, it might report the norm of your residual. Usually this is f. You're solving an equation f of x equals 0. This is f of x at each step. And you can see Newton, what happens is you double the number of accurate digits at each step. That's called quadratic convergence. And so this basically tells you how the solver is functioning real time. So for a linear solver, you might have something like, you don't get quadratic convergence, you usually get linear convergence, which you hope you get another accurate digit after every k iterates. So here it looks like we're getting one more accurate digit after about one more iterate. That would be a convergence factor of 0.1. And what we also see is it's very common to have many levels of iteration. Here we're doing multigrid, so we have a top level, and then we have a middle level here and a bottom level here. And so what we do is go to the bottom, then we go up to the middle, then back to the bottom, then the middle, then the top. This is called an F cycle or a full multigrid. You could also do things that are called V cycles, where you just go from the top to the bottom to the top, or a W, or any of these things. And these have different effects on convergence. I think they're all pretty second order, though, so I wasn't going to go too far into them. What you should be able to see, though, is that each one of these iterations is converging fairly rapidly, and so that is good. What you want to look out for is a stagnation of convergence, where it just sits there and doesn't make progress as it iterates and iterates. And then the last thing that we can look at is the output of this log summary, which is going to show us things about the performance. So here we have a nonlinear solve, a linear solve, which is embedded in the nonlinear solve, and then a setup, which is probably the construction of a preconditioner, like the factorization of the matrix. So we do one Newton solve, 3 Newton steps, each one involves a linear solve, and we do 12 preconditioner constructions, because we count all of the preconditioner constructions on different processors. So this looks like something run on 4 processors, because it did 12 setups for 3 solves. And you can see the time it takes. Boy, I'm not sure why it's getting rid of, on my screen, it's blotting out some of the numbers. But you can see the time it takes, the ratio between different processes. Since the ratio is 1, it means everything is load balanced very well. And you can also see the amount of work done in total flops and the load balance there. And then right at the end of the line, it reports the mega flops done. This is pretty low, but it's a very small problem. So we can also break down these things further. So here we have a nonlinear solve, a linear solve, and a setup. But we can break down the action of the solve into matrix multiplication. So what I said is, when you make that Krylov space, you are multiplying by the matrix each time. If you have a precondition method, you multiply by the matrix and the preconditioner each time. So we're using a preconditioner and a matrix. And then the dot products are done to do projections and compute norms and such. And here, the time for matrix multiplication and inner products is very small compared to the time taken to compute the preconditioner. So it's a very strong preconditioner. And what you see over here is that the megaflops for the preconditioner are quite small compared to the megaflops for the matrix multiplication. So we might be willing to trade more iterates for a weaker preconditioner, because that overall might mean less time. So these are the kind of trade-offs you want to look for, and this is why it's important to be able to read these files at least at a high level. And what you can see over here, this is the global percentages. So percentage of time, percentage of flops, percentage of parallel messages, and the message lengths, and the number of reductions. And so the preconditioner is taking a lot of time. Almost all the time in the solve is taken by the preconditioner, and that's what you can get at a glance here. Whereas a significant number of the flops are happening in the matrix multiply, but it's not taking very much time at all. What? Oh, I went up instead. You can also output this information directly as a Python module using this option, and this will allow you to do automatic processing. Say I would like to make graphs automatically every time I run my parallel job to see how it's doing, and I can output to a Python module, import that module, plot with matplotlib, and throw them up. And I actually do this when I run so that I can monitor effectively what's happening. Okay, are there any specific questions about monitoring or seeing what you have? If not, I'll go on to this discussion of how to stepwise improve what you've got. So the way generally you improve the performance is to take an already running solver that's giving you answers that you believe, and you weaken its convergence, or you weaken the rate at which it's converging to allow higher performance. So let me give you an example. So suppose you're using this GMRes solver, which is, I think, the most reliable Krylov solver. It does a lot of inner products, and it uses a lot of storage. So what you might think about using is something like BiCG stab, which is biconjugate gradient stabilized. That does not have as consistent a convergence as GMRes, but it has far less storage, and it does fewer dot products. So in parallel, it looks much more attractive. And there are several variants of it. So you could change the Krylov solver type to BiCGS very simply, just by giving one option. And this is the idea behind our use of solvers. There is no solver code in PyLith. There is one line that says KSP solve, and then all of the solvers and preconditioners and hierarchical preconditioners and composed solvers, the entire thing is set up from the command line, even when we have multiple fields and when we have interacting solvers. This way, the PyLith code itself is very clean, and we can customize the solver that we use directly to the problem at hand without changing the code at all, which is our goal here. There is a table of all supported solvers and preconditioners linked at this magenta link. Everything that's magenta in these slides is a link that you should be able to click on, and it'll take you to that bit of information. You can do the same thing with a preconditioner like LU. You can weaken it to this is incomplete LU, where you don't do the full factorization, but only part of it, so it has much less storage and smaller amount of work. It's a complicated thing to do in parallel, but you can get third-party packages that try to do it in parallel, like this Hyper, or you can simplify it by only factoring the part that resides on each process, and this is what block Jacobi. Or you can say, well, I'm going to factor the part that's on each process and a little bit of a halo that tends to work much better, and you can get that with these options. we usually like to use a kind of multigrid. I don't think I'm going to go over this comment unless anyone cares about that. We, however, tend to have elliptic problems in PyLith. And elliptic problems, there's a technical definition, but I think the physics definition would be problems that are completely coupled, like Laplace or elasticity or Stokes. If I move a charge somewhere, it affects all the other charges in the problem. If I press on an elastic body, it affects the whole body. In a hyperbolic problem, if I cause a disturbance somewhere, it takes a finite amount of time to propagate to the rest of the thing. So that's a different kind of equation. Here on these elliptic equations, the entire problem is coupled together. And so in order to solve them efficiently, you have to respect the fact that the entire problem is coupled together. And this is what multigrid does. It solves the entire problem on coarse grids so that it's all coupled together, but it's inexact. And then it refines and solves successively more localized versions of that. So that's the idea behind multigrid. And it's pretty simple to write down for structured grids, but it becomes quite complicated when you have an unstructured grid. So what do? And what we do is we use algebraic multigrid for unstructured grids. And there is a built-in algebraic multigrid for PETSC called GAMG. And there's also an algebraic multigrid available from Sandia called ML, although it has now been discontinued in some sense, so it's a little bit wobbly. And then there is a different type of algebraic multigrid algorithm available in the hyper package called Boomer AMG. So remember that I was talking about null spaces. The algebraic multigrid does not work without an accurate null space for your operator. So, for example, for elasticity, you have to provide it with the translations and rotations and say, these are the directions that make very little difference when solving my problem. PyLith will do this for you automatically. But if you introduce something into your problem that has this null space, things can go wrong. So let me give you an example. Suppose what you do is you set up a problem where you have two sides on rollers and the bottom and the top are free. Then you can push that thing up and down without changing the energy of the entire system, unless you turn on gravity or something. And so in that sense, you have a null space corresponding to translation in the up and down direction. And that will cause either a singularity in your problem or ill conditioning, and your preconditioner will stop working. So you understanding these null spaces is worth it when you set up the problem, because they can explain when some things go wrong. So the important preconditioners to be aware of are 1, algebraic multigrid, 2, the field split option. Why is this? If you set up a purely elastic problem with PyLith, algebraic multigrid will work and everyone will be happy. However, as you probably want to do, you want to put some faults in. And the minute you put a fault in, then we do not have a purely elastic problem anymore. We have a problem where we solve for both the elastic displacements and the Lagrange multipliers on the fault, which are your tractions. So what do? Well, algebraic multigrid will not work on this combined problem. It will just, it will fail. It will not be a good preconditioner. But if we pull the problem apart into pieces, into the piece that describes the elastic deformation and the piece that describes the coupling across the fault, then we can apply algebraic multigrid to the elastic piece. We can do something simple for the fault coupling piece and put them back together, and then this can be an effective solver for the entire problem. This is the Schur complement operation. So I will show you the Schur complement operation mathematically coming up. So what it amounts to is separate solves for the different pieces. Here I say block operators, but it's the different equations or different pieces, and you can utilize your physical insight. For instance, I know this is elasticity, and we know what to do there. And you can address each piece using these specific options. And then we have different ways to combine two solves. For instance, what does this mean, additive combination? It means do one solve, do the other solve. So solve for the elastic deformation, then solve for the fault traction, then solve for the deformation, then solve for the fault traction, and go back and forth. If we solve them at once, if we say, okay, solve for the deformation, assuming our initial tractions, solve for the tractions, assuming our initial deformation, then we get additive. If we do them one after the other, so solve for the displacement, use the new displacement and solve for the fault tractions. Use the new traction, solve for the displacement. Then you get multiplicative, which converges faster, but it's serialized in that sense. You can't solve it all at once. You have to solve one piece and then the other. So it's not as parallel. And then the third thing you might do is say, well, I want to solve for the fault tractions, and whenever I need a displacement, carry out that solve. That's sort of the idea behind the Schur complement method. These are iterative. They just approximate the solution. Schur complement is not. It is an exact method for building up the full solution from the pieces. So let's look at what happens. So the Stokes system is a prototypical constrained system. You have balance of momentum on the top here. What is it doing? I don't like this. Okay, let me see if I can get rid of that. Okay, you have balance of momentum on the top, and you have mass conservation on the bottom. So the B operator looks like the gradient, and its transpose is the divergence, and the A operator looks like the Laplacian for Stokes. For our system, A is instead the elastic operator, and B is something that looks like the identity. Actually, it's the turning couples for the fault, right? It's the cosines and sines that come from describing the fault coordinate system, but it's the constraint matrix that says each set of nodes is separated by this distance. So how might you solve this? Well, the most common thing to do is to say, why don't we solve the momentum block by itself and the mass block by itself? And we don't really know how to do the mass block now, so we'll just say, just keep the same pressure and but solve this equation above. And so that is additive combination, and we'll just use algebraic multigrid for the Laplacian, or for PyLith it would be the elastic operator, and then just don't really do much for the pressure. And that was proposed in 1988, although probably used before that. You can introduce some coupling, so you can say, well, why don't we solve the momentum balance first and then use that to correct the pressure. This is multiplicative coupling, so we can again use a geometric multigrid, only this time, algebraic multigrid, but only this time we're going to use a different package. We're going to do the same thing here, but we're going to couple them together. That was analyzed in this paper in 1994. And see, there are just hundreds of papers that you can reproduce completely by giving simple options. That's why this kind of approach is very useful. And I think you can see in the past, when they didn't have this approach, they could get away with writing 100 papers about a thing that we can do in an afternoon. And we can use instead a sure complement approach to stick together the two solutions, and that is that's an exact approach, but if the solvers are inexact, then the result will be inexact. So here, the preconditioner is going to be inexact. We're just going to handle the elastic equations by themselves, and then we're going to do a simple iteration to update the traction block. So what this says is, you know, this sure combination method is exact, but the subsolvers are inexact. And this was proposed in this paper here in 2008, and also this paper here in 2006. The paper in 2008 is specifically a geodynamics paper, so I included it. And we can do better for the subsolvers by combining them together. Here we introduce some coupling between the two of them. You can also do coupling the other way. This, I don't think we need to talk about this. Almost no one does this for geodynamics. But here is the full sure complement. So this is what the word sure complement means. We can factor the original matrix, A, B transpose 0, this way into a product of three matrices. We can factor it into this guy, which shows just the elastic and what's called the sure complement operator, and then these two matrices which couple them together. So if you select sure complement factorization type full, as opposed to, let me go up again just so you can see, as opposed to either diag, or which gives that approximation, or lower gives that approximation, or upper. If you select full, then you get this full factorization. Now this method is exact. So if A is exact and S is exact, this will give the exact answer to the full problem. And here is, and that is what I suggest you do for your initial solves for fault problems. You select a field split preconditioner, sure complement split type, sure factorization method full. You use an LU on A, and you use a Krylov method with a very low tolerance for the tractions, and then you'll get the exact answer to the full problem. And we'll do that in our examples. So I just want to mention that when you're doing this field split stuff, it's advisable at the top level to use flexible GMRes rather than regular GMRes. What that means is that your iterative methods, if you, for instance, use an iterative method for A here or an iterative method for S here that's not exact, then flexible GMRes will maintain the nice convergence rate where GMRes can start to stagnate. Okay, so that is all of the theory about these things, and now we would just get into actually running stuff. Before we start to run things, does anyone have any questions about what I've said before?